Hey guys, so in this lesson we're going to be preparing for our final exam in chemistry, which covers basically everything you've learned so far. So I'll try to make this not a million minutes long, but it will be longer than usual. So hopefully you'll have this handout to take notes on, and you'll need to write everything I write plus some extra stuff. Okay, so how do we prepare for the final exam? Where does the modern model of the atom say electrons are located? It says electrons are located in the orbitals outside the nucleus, or regions of most probable location. We can also describe the position, mass, and charge of protons, neutrons, and electrons. Protons are in the nucleus with a mass of 1 and a charge of 1. Neutrons are in the nucleus with a mass of 1 and a charge of 0. And electrons are in the orbitals with a mass of 0 and a charge of -1. To describe and interpret the gold foil experiment, we would say that alpha particles were shot at a gold foil. Most alphas went straight through, some were bounced off, and the reason for that is that alphas are positively charged, and we now know that the atom has a nucleus, which is small and dense, which makes it able to bounce off some alpha particles, but also that nucleus is positive because it would repel the positive charge of the alpha. If you want to calculate the number of neutrons in an atom, you just need to subtract the atomic number from the mass number. By the way, a mass number is simply the number of protons and neutrons in an atom. The nuclear charge, however, is the charge of the nucleus, which would be the protons in the nucleus. In the case of beryllium-9, while most people would assume that the answer to that question was 9, 9 is actually a mass number. The atomic number is going to be equal to the nuclear charge here, so I looked up the atomic number for beryllium, and it's 4, so I'd said positive 4 as the nuclear charge. The isotope of carbon, which would be the most common, would be the one whose mass is closest to the atomic mass on the periodic table. Carbon's listed atomic mass is 12.0111, I think, so that means that carbon-12 is the most common. So this brings up the concept of isotopes, such as potassium-37 and potassium-42. These are two different isotopes of the same element because they have the same atomic number, or the same element, but they have different mass numbers, or the different numbers of neutrons. So how is K37 different from K42? I will explain using the AZX notation. So the X in the AZX notation stands for the element symbol, so I wrote K in both cases, and the Z stands for the atomic number, and in both cases, potassium has a 19 atomic number. The A is where the mass number goes. So one of them had a mass number of 37, and the other had a mass number of 42. They must have the same number of protons because they're the same element with the same atomic number, but they have different numbers of neutrons, which is giving them different mass numbers. And that is how K37 is different from K42. K37 has 5 fewer neutrons. Okay, let's compare phosphorus 31 to sulfur 32 using some of these same skills. So phosphorus 31 is going to look like that. Its atomic number is 15. And sulfur 32 is going to look like this with an atomic number of 16. That means that this guy has 16 neutrons, and I can tell that because I'm doing 31 minus 15. And the sulfur seems to have 16 neutrons as well, because I'm doing 32 minus 16, and I'll use this information in the table above. So the number of electrons for phosphorus 31 is going to be equal to its number of protons, and phosphorus has 15 protons. So 15 protons and 15 electrons. For sulfur, it's going to be the same thing, but the sulfur has 16 protons and 16 electrons. The number of neutrons I calculated earlier, they're down here, so 16 neutrons for each one, and that's how I would compare and contrast phosphorus and sulfur. Okay, let's do the ground state electron configuration of an aluminium atom, which is the fancy British way of saying aluminum. I looked it up to be sure, but it's 283. I'm going to list one possible excited state, and the way I'm going to do that is I'm going to take one electron from this full orbital in orbital 2, and I'm going to toss it up into orbital 3, which is unfilled. And I would say that the easiest one to write and understand here would be 274. What happens to the energy of an excited electron when it returns to ground state? So after this excited state, the one electron here will shift back down and it'll return to this state. And in that process, of course, it releases energy in the form of light, typically. Okay, so we can tell the difference between fission and fusion when we're looking at a nuclear reaction equation, because a fission reaction will have two major products on the right-hand side of the arrow, whereas a fusion reaction would have only one major product. So since we're on the subject of nuclear chemistry, this brings up half-life. Half-life is actually an amount of time, and specifically it's the amount of time required to for half of a sample to decay. Let's do an example. Based on reference table N, what is the fraction of a sample of potassium-42 that would remain unchanged after 62 hours? So I checked table N, and the half-life for potassium-42 is 12.4 hours. We can use that to construct our answer. So the total amount of time that the sample has been decaying is 62 hours, and every 12.4 hours, half of it decays. So I'm going to figure out how many times 12.4 hours goes into 62. So I just did that calculation, and I can see that 12.4 goes into 62 5 times, which means that there were 5 half-lives that have passed since the beginning of the decay. One thing you need to know is that every time a half-life passes, you lose half the material, which would mean that after one half-life, you'd have only half of the original, and after 2 half-lives, you'd have only half of that half. After 3 half-lives, you'd have half of half of half. After 4 half-lives, you'd have half of half of half of half. And after the 5th half-life, you would have half of half of half of half of half. So when you put all of that together, the fraction that remains is 1 over 32. And the way you get that answer is by multiplying the denominators by themselves. So it's like 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And that's how you get the final answer, 1 over 32. So when nuclei change, we can describe their decay using half-lives, and we can also judge the charge of the particles that are exiting a nucleus by putting them through an electric field. So that's what's going on in this diagram. We have the positive part of the field at the top and the negative part of the field at the bottom, which means that all of the particles that would travel towards the positive field would be the ones that have a negative charge because opposites attract. And the particles that would travel towards the negative field would have a positive charge. Again, same reason opposites attract. And the particles that would take pathway 2, which is towards neither field, would have no charge. So I put in the particles that I think match those characteristics. So on pathway 1, I have all my negative particles, which is just the beta. Pathway 2, I have my neutrons and gammas, and pathway 3, I have my alphas, my protons, and my positrons. The nuclear emission that has the greatest mass is definitely alpha with a mass of 4 and a charge of 2. Which radioisotope is most often used for dating organic remains? Organic means that it is like a living thing or was a living thing, and that means that we would be using carbon-14 as the radioactive isotope. Particle X. We can determine what particle X is by using some algebra for the masses and the algebra on the charges, and we'll be able to figure out the mass and the charge of particle X. I can tell you for certain that On the right-hand side, the masses are adding up to 10, so they must add up to 10 on the left as well, which means that the mass of X must be a 9. On the right, the masses add up to 5, so they must add up to 5 on the left as well. So that means that the charge of X must be a 4. So if we have a particle X whose mass is 9 and charge is 4, then what we're really talking about is beryllium-9. And I chose beryllium because the atomic number has to match the element. Okay, number 17. In nuclear reactions, the mass of the products is always less than the mass of the reactants. This seems to disobey the law of conservation. But the mass defect says that matter is always converted into energy. And therefore, if matter is being converted into energy, then it's not being lost, and therefore the law of conservation is not being broken. All right, number 18. We're going to describe the position of each of the following groups on the periodic table. So metals are first up, and I usually just say that metals are in the lower left. Non-metals are in the top right. Metalloids will border the staircase, but there are 3 exceptions. Aluminum, polonium, and astatine are not metalloids, and the only elements that classify correctly as metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium. And noble gases are in group 18. All right, and electronegativity and ionization energy are related, so I'll do those together. Electronegativity is the desire an atom would have to gain an electron, while ionization energy is the amount of energy needed for a third party to remove an electron. Generally, when one atom has a high desire to gain an electron, or a high electronegativity, it also has a large resistance to losing an electron, which would be a high ionization energy. So those two usually go together. The exception would be for noble gases. The noble gases would have no electronegativity because they don't want to gain electrons, and they also would resist the loss of electrons very much. So in the case of noble gases, they have high ionization energies, but low electronegativities. So electronegativity would increase as you go up and right in general. It basically follows the trends of decreasing radius for atoms. And ionization energy will increase as you go up and right in almost every case. Atomic radius will decrease as you go up and right, and metallic character will decrease as you go up and right. Properties of metallic solids would be that they're conductive of heat and electricity. They have luster, meaning that they're shiny. They're also malleable and ductile, and they have high melting points. So speaking of their conductivity, that's caused by their mobile sea of electrons. Non-metallic solids, on the other hand, would be pretty much the opposite properties. They would be non-conductive, dull, with low melting points if solid, and they would be brittle if solid. So this next bit is to help you understand and to explain why radius decreases as you go across a period. As you go across a period from left to right, the number of protons increases, yet the number of shells of electrons remains the same. And when those two properties, I suppose, interact, it means that as you move to the right within a period, the shells of electrons will contract as a result of increased attraction for the nucleus, and that would mean that the radius would decrease as you move from left to right within a period. But as you go down a group, there is more happening than just adding protons. If you go down a group, you're also adding shells of electrons. Therefore, you would notice that the radius increases, even though the number of protons is also increasing. It does explain why bromine is a larger radius than fluorine, because bromine has more shells of electrons. I have one more thing to add about elements that are in groups, which is that elements in the same group have the same number of valence electrons and therefore would have similar chemical properties. While we're on the subject of electrons, covalent bonds are formed by sharing electrons, whereas ionic bonds are formed through transferring electrons. And there are two types of covalent bonds. They can be polar or nonpolar. The polar type of covalent bonds are a result of a difference in electronegativities between the two atoms that are bonded, whereas the nonpolar type would be two atoms of the same element that are bonded together and therefore have no electronegativity difference. And it also brings up the idea of a polar molecule or a nonpolar molecule, which doesn't have to do with electronegativities as much as it has to do with the symmetry or asymmetry in the molecule itself. A symmetrical molecule would be nonpolar, and an asymmetrical molecule would be polar. So let's think of some examples. For instance, how about a polar molecule that contains a polar bond? An example there could be HF. The molecule itself would be polar because it's asymmetrical, and the bond between the H and the F, right here, would be polar because the fluorine, with its larger electronegativity, would pull the electrons to this side of the molecule. All right, next example, a nonpolar molecule containing nonpolar bonds. A good example would be a diatomic molecule, such as nitrogen. It would have a nonpolar bond because of the electronegativity difference of 0 between the two atoms, and the molecule would be nonpolar because of its symmetry. And a good example of a nonpolar molecule containing polar bonds could be carbon dioxide. The molecule is nonpolar because of its overall symmetry, and the bonds, the double bonds here and here, are polar because of the difference in electronegativity between the carbon and the oxygen. The oxygen is more electronegative, and the electrons would be pulled to the outside of the molecule, away from carbon. Okay, the class of element that has ions larger than atoms would be nonmetals because they gain electrons when they ionize. In terms of potential energy and stability, what happens when bonds break? So when bonds form, stability increases and the energy decreases. So when bonds break, stability would decrease and the potential energy would increase. As I just said, when bonds form, energy is going to decrease. So when two iodine atoms bond to form a molecule, energy would be released. How many electrons does an oxygen ion have? Show your work. Well, an oxygen atom, which is where we would start with this, would have an electron configuration of 2,6, or it would have 8 electrons. But it would gain 2 electrons to fill the valence shell, so that it has 8 in the valence shell. So its new configuration would be 2,8, which would mean that you would have 10 electrons in total. So let's draw a Lewis dot structure for the above ion. Since it is a nonmetal, you pretty much always do the same thing. You just need to have 8 electrons around it in pairs with brackets and an appropriate charge. But a Lewis dot structure for the ground state atom would look somewhat different. You would only do the 6 electrons in the valence shell rather than 8, and the first 2 go together. And after that, you alternate sides, so you would have the third one here, the fourth here, the fifth there, and the 6th would come back up and pair up. But you would have 2 unpaired valence electrons. Now, the type of bonding that would be found in all molecular substances is called covalent. And this also means that the definition of a molecule is any substance that is completely bonded covalently. Let's draw a Lewis dot structure for carbon dioxide and explain in terms of structure and distribution of charge why it's nonpolar. So it would be nonpolar because it has an asymmetrical structure, or you could say it has an equal distribution of charge. Now for a bond, we can talk about its polarity, and the degree of polarity in a bond would be judged based on its electronegativity difference. The larger the electronegativity difference, the more polar the bond would be. Let's draw a Lewis dot structure for CH4, methane. This molecule would not be polar because it is symmetrical, but it does contain polar bonds because there is an electronegativity difference between the carbon in the center and the hydrogens on the outside. So the electrons would be drawn closer towards the carbon. So in terms of intermolecular forces, what you need to know is that the larger the intermolecular force, the more attraction you have between particles, and therefore it would increase things like melting point and boiling point. So in short, the more intermolecular force, the higher the melting point and boiling point. All right, on to Unit 5. As for solids, liquids, and gases, in terms of their particle movement and their arrangement, solids vibrate around fixed positions. Liquids are spaced apart a little bit more than solids, and they also have the ability to flow. Gases would be moving in all directions, very far apart from each other. Solids would have their definite shape and definite volume. Liquids would have a definite volume but an indefinite shape, and liquids have an indefinite shape and an indefinite volume. So exothermic phase changes are anything that you would find on a cooling curve. So some examples could be, let's say, from gas to liquid, and also from liquid to solid. But you would have deposition as well, which would be the one that goes from gas all the way to solid. Likewise, the endothermic phase changes would be anything that you might find on a heating curve. So we have our melting phase change, we have boiling, and the one that goes straight from solid to gas, that's going to be sublimation. Sublimation is the phase change from solid to gas. So I'm going to give you a rundown of the heating curve. As you go from A to B, you're increasing kinetic energy. B to C, you're increasing potential. C to D, increasing kinetic. D to E, potential, and E to F, kinetic. In every case, in every one of those segments, only one type of energy would increase at a time. So if something is increasing, the other thing is staying the same. All right, so for the cooling curve, I can do something very similar, but I, in this case, actually just want to talk about the phases that are present in each segment, just to sort of cover all my bases here. So from A to B, we have gas only. B to C, we have gas transitioning to liquid. C to D, we have liquid only. D to E is liquid transitioning to solid, and then EF is going to be solid only. So we need to do an example of Q equals MCAT. And what I would point out is that Q equals MCAT requires a temperature change calculation, so you would only be able to use it in segments like A, B, C, D, E, F. Same thing here, A, B, C, D, E, F. And the reason why you cannot use it here, 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 or here is because those are phase changes where temperature is not changing. So let's get started. What's the total number of joules lost when 10 grams of water at 80 is cooled to 60 degrees Celsius? So I multiplied 10, which is the mass, by the specific heat capacity of water, which is 4.18, and the difference in temperatures, which is 20 degrees, and I got 836 joules. Let's do an example of Q equals MHF, which you would only be able to use here, BC, or here, DE, and that's because BC represents a melting phase change, whereas DE represents a solidification or freezing phase change. So those are the only two cases when you would use Q equals MHF. So I multiplied the mass of 10 by the heat of fusion for water, which is 334 joules per gram, and I got 3,340 joules. All right, final example. Let's do Q equals MHV, because here's the question: what's the number of joules needed to change 40 grams of water to vapor at the boiling point? Show your work. So I multiplied 40, which is the mass, by 2260, which is the heat of vaporization for water, and I got 90,400 joules. which could be represented a couple of different ways. I divided it by 1,000 first to get 90.4 kilojoules, and then I converted into scientific notation and got 9.04 by 10 to the 4 kilojoules. All of those things are appropriate, it just depends on your answer choices. So let's talk about the definition of temperature. It's a measurement of the average kinetic energy of the particles of a substance. It is not, however, a form of energy. It's just a measurement of average energy. Okay, so the temperature of a sample of copper increases by 10 Kelvin. By how many degrees Celsius did the sample change? It would be, of course, 10 degrees Celsius of change as well. And what you should be picking up on here is that 1 degree of Celsius is equal in size to 1 Kelvin. So they have the same size. Let's convert 0 Celsius to Kelvin. So I just used the equation that was on my reference table, and I got 273 Kelvin as my answer. So the kinetic molecular theory has 4 parts, and all of them you have to memorize. So I just added them in. I just noted that particles move in random straight lines and that they're small and distant from one another. They are not attracted to one another in any way, and they collide with each other, but when they collide, their collisions are elastic, meaning that they transfer energy perfectly. So those are the 4 tenets of the KMT. Make sure you know them. We'll have to do an example of combined gas law. The data is here in the question. I am going to label it and come back. So I really only found 2 temperatures and a pressure. We're going to look for the second pressure, and they told me that the volume of the light bulb remains constant. So I'm going to take the volume part out of the equations here, and we'll just have P1 over T1 is P2 over T2. We're trying to show a correct numerical setup for the pressure, so I circled pressure to indicate that we're going to be looking for it. I'm going to isolate it now. I'm choosing to multiply by T2 on both sides to cancel the T2 on the right, and that will give me a new equation that looks like this. P2 is T2 P1 over T1. And I can just put in variables from here. My T1 was 295 Kelvin. Let's see, my T2 was 418 Kelvin. And my P1 was 75 kilopascals. So there's my correct numerical setup for calculating that second pressure. Alright, so I'm going to label some axes and draw a graph for each of the following relationships. Those relationships are pressure, particles versus pressure, temperature versus pressure. They're like the individual things that make up the combined gas law. The only one of these relationships that isn't direct is the pressure versus volume one, and that's because pressure and volume actually have an inverse relationship up here in the numerator of the equation. Let's discuss ideal gases versus real gases. The definition of an ideal gas is one that follows the kinetic molecular theory perfectly. We don't really have ideal gases, but the 2 best gases for the kinetic molecular theory that we do have are hydrogen and helium. And if you wanted to promote the ideal behavior from any gas, what you would do is you would lower the pressure and increase the temperature. Okay, so on to separating mixtures. Homogeneous mixtures are notoriously difficult to separate because homogeneous mixtures are very evenly mixed. An example could be salt water, whereas a heterogeneous mixture is unevenly mixed. An example could be sand and water. We can use filtration to separate heterogeneous mixtures and never for homogeneous mixtures. But for homogeneous mixtures, we might use distillation or evaporation to separate the particles. So, examples. If a student pours a mixture of sand and salt water through a filter paper and into a beaker, what would be found in the beaker would be the salt water. And the reason for that is because the salt would be dissolved in the water homogeneously, and that cannot be filtered. So it would pass through the filter and be in the beaker. Now, in the filter paper, what would be filtered out would be the sand. It's impossible to separate a dissolved salt from water using a filtration setup because they are homogeneously mixed. So as I said, homogeneous mixtures are more difficult to separate, but they can be separated using setups like distillation. And it's possible because you would choose to separate substances that have different boiling points. And that concludes my review for the fall semester final exam. I do recommend putting in some more studying of your own in a method that really matches your learning style. But this was just a way of reviewing some of the basic content that may be on the exam. Thanks for watching. Good luck, and be calm and be confident that you have this in the bag. You're great. You're going to be great.